Hello everyone, we are Group 3 and our project is TriForce Walker, a spring-powered three-legged in-pipe robot. I'm Çağatay.
I'm Berk.
I'm Selin. This robot is designed to move through narrow pipes or ducts, making it useful for inspection and maintenance in hard-to-reach places where normal wheeled robot can't work well. We started with a simple but functional design. The spring-loaded three-leg system maintains constant wall contact, allowing the robot to work in 47, 54 cm pipes and climb inclined or even vertical surfaces.
The first problem that we encountered was the unwanted rotation occurring between the two cylindrical components of the leg design. Due to the telescopic design, the cylinder and piston were rotating between each other. There were some number of solutions to that. However, since our robot can climb inclined surfaces, we changed the shape of the piston to square without having any additional weight. The second problem was the fracture of the leg. Since we were planning to squeeze the robot inside a tube, we only thought that the piston would only carry tensional load due to the compressed spring. But when we extended the robot by itself for the first time, the weight of the leg caused bending stress and our piston fractured from the top side. For solving that, the first thing we did was to add edge balance of 5 millimeters to the fractured part, and also we increased the infill rate of the material from 5% to 50%. In here, you can see the final CAD model and final robot. We used special custom springs in this project. According to the CAD models and ANSYS analysis, we selected our spring dimensions and found a custom spring manufacturer in Bayrampaşa and produced our springs. Since these are not mass-produced springs, we calculated the spring coefficients via using a dynamometer and Hooke's law. Under 3 centimeters of extension, our springs resulted in a force of 15 Newton, and our spring coefficient turned out to be 556.3 Newton over meters.
At the beginning of the project, we couldn't find a wheel on the market that matched the dimensions we needed, so we decided to produce our own wheel. We designed the CAD model of the wheel mold and printed it with a 3D printer. Then we cast it with VRM2 silicone. However, the PLA material we used wasn't strong enough to withstand, and this wheel eventually broke. As a result, we had to look for an alternative solution. We found a suitable wheel at a hardware store that sells wheelbarrow parts. However, while our motor shaft had a 6 mm radius, the wheel's inner diameter was 8 mm. To solve this, we had a custom adapter manufactured using a latte outside the university. This adapter allowed us to connect the motor shaft and wheel securely.
As Berk mentioned earlier, we had to replace the wheels. The custom-made wheels showed high stress at the motor shaft connection point, which we confirmed through ANSYS simulation. As seen in the figure, the new metal wheel reduced the stress in that critical area. We analyzed critical PLA part of the leg exposed to compressive load. Stress concentrated near the inner mounting area, so we increased wall thickness and infill. As shown on the screen, the stress remained far below PLA's yield strength of 56 megapascal. Motor caps were also analyzed due to their exposure to screw and shaft load. The stress values of parts remain very low and well below PLA's yield strength. In any case, flat washers were added to improve load distribution.
On the left, you can see the complete circuit diagram. The central controller of our system is Raspberry Pi 4 Module B, which sends control signals to 3 motor drivers. Each driver operates 2 motors, totaling 6 motors for our system. We also integrated an MPU 6050 sensor, which provides real-time gyroscope and accelerometer data for balance and orientation control. The system is powered by sufficient LiPo. For visual monitoring, we use Logitech camera, which streams video to the user interface in real time. On the right side of the slide, you can see the summarized bill of material. We use several Python libraries: Pygame for building the interface, GPO0 for controlling motors, OpenCV for live video streaming, NumPy for numerical processing, and MPU 6050 library to read sensor data such as roll, pitch, yaw, acceleration, and gyroscope values in all 3 axes. The interface displays real-time sensor data, motor states, and a live camera feed, allowing us to control and monitor robot during the operation. On the left side, you can see our first test evaluating the motion capability of each leg individually. On the right side, we tested the robot inside a pipe for the first time and concluded that additional stability was needed, which we achieved using ball caster wheels. These videos demonstrate the final performance of our robot in both horizontal and inclined pipe tests. We are proud to state that we have successfully achieved all the objectives we proposed at the beginning of the semester and more. As a potential future work, this can be added. Autonomous stabilization with PID, rotation capability of legs, adding image processing. Here is our thank list, and thank you for listening.